In today's lesson, we're going to consider looking at confidence intervals, and in particular, we're going to look at confidence intervals when we have a large sample and we're looking at the population mean or the population proportion. So we saw in the introduction to confidence intervals what happens if we have a population which is exactly normally distributed, and we worked out how we could find a confidence interval for the mean of the population when we know the variance. So we're going to continue that type of process and look at some different scenarios here. And so in today's lesson, we're looking at large sample, and then over the next few lessons, we'll look at a few different scenarios as well. So we want to, in today's lecture, learn how to construct confidence intervals for normal population means when we have large samples without a known variance, and we also want to construct confidence intervals for the sample proportion in large samples. Now, before I begin today's lecture, I want to make a quick disclaimer on introductory statistics education. The next few lessons, we're going to be looking at confidence intervals in different settings. And then following that, we're going to be looking at what are known as hypothesis tests. And we're going to do a similar process to what we've done with confidence intervals, where we talk about it generally, and then we look at a bunch of specific settings. Now, I think it's important to see all of these specific settings for the confidence intervals or for the hypothesis tests, because these are going to be the areas that we're actually most commonly applying confidence intervals. But I think that there's a tendency, especially in an intro stats class, to teach these as though they are separate from one another, or as though you need to learn these procedures as a standalone thing, when in fact, all of the information about the confidence intervals were shown in the last lecture, and now we're just sort of applying those techniques to cases that we might care about. So there's going to be a lot of repetition over the next few classes, but what I would emphasize here is that the specifics here are not recipes to memorize and then figure out when you're applying each of them. I really think that it's more important to be able to reason through when you should be building confidence intervals in different types of ways, and to understand sort of how are we getting here. And really how we're getting here is through that process that we talked about last time. So I'd like to sort of put forward the next few lessons as examples of that, rather than as unique pieces of information to learn in and of themselves. So in the last lecture, we made the unrealistic assumption that the variance of our population was known. When it's not known, we need to address this somehow. And so sort of a natural possibility to think about is what happens if we replace the population variance, sigma squared, with s squared, our sample variance. If we do this in general, we render the statistic that we care about to be non-normal. And so in particular, what I mean is that if we take z, and zoom in here, z to be the sample mean minus mu divided by s over the square root of n, where before this value would have been a sigma, this is not going to be normally distributed. We'd have 0, 1 generally, right? So this is not going to be the case, at least in general. However, if we take n to be very large, if we take n to be sort of big enough that the central limit theorem starts to apply, then we can say that this statistic here is going to be approximately normal. So you'll notice that we have our dot above the tilde. What that means is this distribution isn't exact, but as n becomes larger and larger, this becomes a close enough approximation. Okay, so when n is large, we can say that this normal approximation holds. And if we're willing to say that the normal approximation holds, well then, of course, we can take exactly the same process that we took last time in order to form a confidence interval. So let's just remember what that process was, right? So we said that we can find two values, a less than or equal to x bar minus mu for s over square root n, less than or equal to b, such that this is going to equal 1 minus alpha, right? And then we can find a and b as the critical values from our normal distribution here. So a is z of alpha over 2, b is going to be z of 1 minus alpha over 2. And then we take these and we solve for x bar, or sorry, solve for some function of x bar. So I'll say solve for mu in an interval. We called that lower and upper last time, right? And this is how we get our confidence interval. So we can apply the exact same procedure here. And in fact, because we're still working with this normal population, it's going to be literally the same, except replacing sigma with s. So if n is not large enough, the argument that we're making here does not hold, and we'll see that situation before. But if we're willing to say this is approximately normal, then we get the same confidence interval. So if we work through that argument exactly the same as last time, we find the probability being between the critical values is approximately 1 minus alpha. So we can take the lower bound to be x bar minus the statistic, and the upper bound to be x bar plus the statistic. And then we get the same sort of form for the confidence, which is x bar plus or minus the alpha over 2 level confidence level. And here we're just replacing sigma with s. We can still use this to determine sample sizes if we have an estimate for s, right? So we can still use the margin of error there to invert this and say we need the sample size to be whatever value, right? So in this sense, the procedure is literally exactly the same one that we saw last time. And the important thing that we found was that the sampling distribution is still going to be approximately normal. So the only thing that mattered for this was that our sampling distribution was known. We took those critical values and used the same process. If we don't know s, or we don't have an estimated value for s, then we could take sort of a conservative guess as to what it would be. The larger that s is, the larger sample size we're going to need. And so if we just take a value that we think is sufficiently large, that will work for sample sizing. Now, we can also think about what happens with the population proportion. And I'll come back here and make the same sort of argument that we were just making. We said that if we have sort of the correct values for n and p, so if n is large and then p is around 0.5, then if x is distributed as binomial np, then we have that x is going to be approximately distributed as a normal with n times p, and then n times p times 1 minus p, right? And so what this means is that if we go 1 over n times x, which is what we've defined to be the sample proportion, right? X is the total number of successes, so you divide that by the total number of trials to get the sample proportion. Well then, based on sort of the properties of our expectation and our variance, then what we're getting is that p hat is going to be approximately distributed as a normal random variable, where, remember, if you're multiplying by a constant, you multiply the expectation by that constant. So it's going to be normal centered at p. And then with the variance, you multiply that by the constant squared. So it's going to be 1 over n squared, or p times 1 minus p divided by n, right? And so then what this means is that if we take p hat and we standardize it exactly the way we just standardized the sample mean, so we take p hat minus p, divide this by the standard deviation, so that's going to be the square root of p 1 minus p divided by the square root of n, right? Then this is going to be approximately distributed as a normal 0, 1. And so from this approximation, we can use, again, exactly the same procedure that we've been using. Okay? So here, we just walk through how we approximate the sample proportion as a normal. And the exact same arguments on the last page are going to give now the confidence interval for the population proportion is going to be our sample proportion plus or minus the critical value times by the standard error, which in this case is the square root of p times 1 minus p over n. Okay. Once again, we can use the same procedure to do sample size calculations. In the case of the sample proportion, the worst that we can do is if we take p equals 1/2, right? So if we're looking at the variance, p times 1 minus p is maximized at p equals 1/2. And so because of that, if we wanted to be as conservative as we could be, then taking p equals 1/2 is going to give us the most conservative estimate. But otherwise, we can just use our estimated value, we'll plug it in, and this is going to be approximately correct whenever this approximation sort of holds. So again, if p is not known and we're trying to do sample sizing, taking p equals 1/2 is going to be conservative. So in summary, if the variances are unknown, but we have a big sample, we're still going to be able to pull out the normal approximation, and then we can just rely on what we did in the last lecture. If we're estimating the population proportion and the normal approximation holds there, then we can use the same argument for the normal approximation. So once again, I'll emphasize that in this lesson and in the coming lessons, we're going to keep looking at these different use cases for confidence intervals, but I'd emphasize to make sure that you're very comfortable with how confidence intervals are formed in general. And once you're there, what we're talking about in these lessons should be very clear. And so I hope to see you all in those next lessons.